Okay, this is a solution for number 7 in energy. A billiard ball, a pool ball rolls down a ramp that's half a meter high, and at the bottom it runs straight into another billiard ball um, that's initially at rest. Okay, so uh, we have one of these balls that starts up here. Um, and it rolls down this ramp. We don't have to know the shape of the ramp, and runs into another ball at the bottom. By the way, I mentioned in one of my recent calculations that um, we're losing uh, some accuracy in this problem if the thing is rolling. So really, this makes more sense for if this was ice and this thing was free to slide down. That seems like sort of a nitpicky thing, but you have to deal with energy of an object starting to change its orientation as it rolls down the hill, and that will be something. But um, anyways, back to this problem. So let's imagine that it's sliding down, and then we don't have any problem with that. And this height is half a meter, and it rolls down the hill, crashes into another one of these billiard balls that actually they have different masses. I don't know what kind of billiard balls these are, but um, so this one has a mass. Why is it doing that? Okay, this has a mass of 0.15 kilograms. The one at the bottom has a mass of 0.25 kilograms. The one comes down the hill, smashes into the other one, and they bounce apart. And we want to know the velocity of the first ball right before the collision, and then we want to know the velocities of both of them after the collision. Okay, so for part A, to calculate the velocity of the ball that starts at the top of the hill right before it collides with the second one, what we're doing is it's a problem that relates a change in position of an object to a change in speed. So that's something we're going to use conservation of energy for. The collision hasn't happened yet. We do know that when we get to the collision, we're going to have to use conservation of linear momentum for that. That always is the way to deal with collisions. All right, so let me start by drawing a free body diagram of the ball. Um, there's a normal force, there's a weight force, um, and those are the only forces acting on it before the collision. Again, going back to this rolling versus sliding thing, if it's sliding, these are the only forces on it. If it's rolling, there's actually a friction force that's holding the bottom back relative to the top, and that's what you can think of as like, okay, if it's going to be rolling, that friction force um, is going to do work, and we can't use this approach this way. Okay, well, the normal force is non-conservative, uh, but it does no work, so that's okay. The weight force is conservative. We have a potential energy function for that, so we know we're good. We can use conservation of mechanical energy. I'm going to say instant 1 is at the top of the hill, and instant 2 is at the bottom. There's no springs, so the only potential energy we have to deal with is gravitational. Um, and the gravitational potential energy is m times g times the height. That means we have to choose a reference height equals 0, and I'll choose that down at the bottom. You could choose it anywhere and you'd get the same answer for the speed. You just have to be consistent through the problem. Okay, so the potential energy at the top is the mass times 9.81 meters per second squared times the height, which is 0.5, and you get 0.73 736, I'll call it. That's in SI units because everything's in SI units, so this is in joules. And the kinetic energy, it's at rest at the top of this hill, so the kinetic energy is 0 because the speed is 0. And then at instant 2, when it's at the bottom of the hill, the height is 0, so the gravitational potential energy is 0. And the kinetic energy is 1/2 times the mass, 0.15, times the speed squared, and we don't know what that is. We're trying to find the speed. So conservation of mechanical energy says if you add these up, they have to equal each other. And so you get the V is equal to plus or minus 0.736. Hold on a second. Divided by 0.075. That's 9.81 because some masses cancel and stuff. And then take the square root of that. And you get 3.13. This is the speed, so we want the positive one. And so right before these two billiard balls collide, the speed of the one that starts at the top is 3.13. Okay, now for part B, now we're going to deal with the collision. The net force, if you take those two balls as a system, the net force on that system is 0, and that means we can use conservation of linear momentum for the collision. And so I'm going to add up the linear momentums of the two balls before the collision and add them up after the collision. To do this, we have to think about what kind of collision we have. Billiard balls are sort of classic examples of elastic. Collisions between billiard balls are elastic. They bounce apart without losing very much energy. And so we're going to use the conservation of linear momentum and also use that requirement for elastic collisions that says the kinetic energy of everything, you add it up before the collision, is equal to the sum of all the kinetic energies after. Okay, so conservation of linear momentum. So now if you look at this picture, they're both just moving horizontally, and I'm just going to use the horizontal component. I'll call it the X component. So right before they collide, we have the one ball with a mass of 0.15 kilograms times its velocity, so it's moving in the positive X direction with that component of velocity. And then we have the second one with a mass of 0.25, and it's at rest before the collision. After the collision, the one that's 0.15 kilograms, we'll say that that's moving with a velocity v1, and the one that's 0.25 kilograms is moving with a velocity v2. I'll simplify this. I'm going to divide everything by 0.15. So we get 3.13 is equal to V1 plus, that's 5/3 V2. And I'm going to get V1 by itself, you know, just because I've done a million of these, I know that that's what I'm going to do, but you really don't have to do this. You can do it when you get to it. The key thing is you get one equation out of conservation of linear momentum, and then you're going to solve it as a system with the one equation you get out of the kinetic energies being equal before and after. So V1 is equal to 3.13 plus, I'll call this 1.6, 1.6 repeating V2. Okay, so there's our first equation. Now it's elastic, and that says that if you add up the kinetic energies before, it equals the sum of the kinetic energies after. So the kinetic energy of the ball that's moving before the collision is 1/2 times the mass times its speed squared. Kinetic energy of the second one before the collision is 0 because the speed is 0. After the collision, we have 1/2 times 0.15 V1 squared plus 1/2 times 0.25 V2 squared. And I'm going to divide everything. I'm going to get rid of the halves, divide both sides by 1/2. Divide everything by 0.15. And 3.13 is 9 squared is 9.81. That's equal to V1 squared plus 1.6 repeating V2 squared, and I'll call that my second equation. So that's 2 star. Okay, and now we just have to solve this system of 1 star, 1 star and 2 star. Take the simplest of the two equations, that's 1 star, substitute it into the more complicated one, and just solve this system. So from 1 star, you get V1 squared is equal to 3.13 squared plus 2 times 1.6 repeating times 3.13 V2 plus 1.6 repeating V2 squared. And I'll simplify that. So V1 squared is equal to 9.81 plus oh, and I just noticed this has to be squared too. I forgot to do that. Okay, so the second one is 10.43 repeating V2, and the third one is 2.7 repeating V2 squared. And so now we can plug that into 2 star. And we get 9.81 is equal to all of this stuff that's equal to V1 squared. plus 1.6 repeating v2 squared. For a lot of these problems, I guess all the problems where one of the objects is at rest before the collision, you get a cancellation of the constants. And so we get 0 is equal to so we have 10.43 v2 plus oh, this isn't positive. Okay, I got to fix some stuff. Okay, equation star. I had it wrong before. So this is going to, that means that, what's that going to change? That means that this is negative, and that means that this is negative, and that means that this is, no, that's not so bad. So this is negative 4.4 repeating v2 squared. Okay, and now you can solve this by factoring 0 is equal to v2 times the quantity v2 minus 2.35, let's call it. Yeah. Okay, so the only way you can, the only roots are if v2 is 0 or the stuff in parentheses is 0. So v2 is equal to 0 or positive 2.35 meters per second. One of those two represents what object 2 was doing before the collision. We don't want that. We want to know what's happening after the collision. So after the collision, that second, more massive ball is moving with a speed of 2.35, and we got a positive value, which means it's in our positive x direction. It's going toward the right. Now we can plug that into any other equation that, the easiest one that we can find to figure out what v1 is. I guess that's equation star. So v1 is equal to 3.13 minus 1.6 repeating times v2, which is 2.35. And you get that v1 after the collision is negative 0.78, 79, I guess, if you round it. Okay, so what happens? The lighter ball rolls down the hill, picks up speed, runs into the heavier ball. It makes the heavier ball take off to the right, and because the ball that went down the hill is the lighter of the two, it doesn't even just stop dead. It actually starts going back in the direction it came a little bit. Okay, so that's the solution to number 7 from energy.